Hi, I'm Jeff Groh, and this is Differential Equations, Exam 1 Review. My exams generally look like this. I'll scroll down so you can see more of what the practice exam looks like. This is the practice exam that we'll be going over today. You can see that we have an array of problems. And that's it. The first problem on the review is x, y prime, plus 2y equals e to the x. This is first order linear, and so we need to put this into standard form first. So we'll divide by x to begin with. If we divide everything inside by x, we put this into the standard form y prime plus 2 over xy equals e to the x divided by x. Now we need to calculate the integrating factor mu. Mu is e to the integral of p of x dx. The general standard form is y prime plus p of xy equals q of x. So in this particular problem, p of x is 2 divided by x. And so we end up with e to the power of the integral of 2 divided by x dx. And that's e to the 2 times the natural log of x. Now, remember that on the integrating factors, we don't need to worry about absolute values on the logs or plus c's. In order to cancel the e and the log, we first have to move the 2 up. And so this is going to be e to the log of x squared. Now the e and the log cancel, and the integrating factor is x squared. With our integrating factor of x squared, you need to remember the formula now. Y is 1 over mu, the integral of mu q plus the constant of integration divided by mu. So on this particular problem, we have 1 over x squared, the integral of x squared e to the x divided by x dx plus c divided by x squared. And remember that the q that you use is from the standard form after we divided by the x here. You have to divide e to the x by x, and that's why we ended up with e to the x over x here. This x will cancel with one of those. So we're really integrating just x e to the x. With y is equal to 1 over x squared, the integral of x e to the x dx plus x squared the method of integration is going to be integration by parts, because we have a part that we'd rather differentiate and another part that we can integrate. So if we set this up with just the tabular method, we'll have x and e to the x. Continue this down. 1 and then 0 are the derivatives. Derivative of x is 1. The integral of e to the x is e to the x. We integrate down the second column. 1 over x squared times, remember that you multiply down diagonals and you alternate signs, so this is plus and then minus. So we get x e to the x minus e to the x plus c divided by x squared. And this is the solution to the differential equation. For problem 2, differential equation is y prime minus 1 over xy equals x times the sine of x. It's already in standard form, so we'll just calculate the integrating factor mu, which is e to the integral. Be careful. The negative here is part of that p of x. A lot of students will leave that negative off. And even after putting the negative here, a lot of students will misunderstand how to deal with it. We get minus natural log of x. Now you can't just cancel the e and the log, you have to move the negative first. So we need to write this as e to the natural log of x to the power negative 1. This negative 1 can move up as an exponent on the x. At this point, the e and the log cancel, and the integrating factor is 1 over x. Using the formula for the solution, y is 1 over mu. 1 over x is x, times the integral of mu q plus c divided by mu, but if you divide by 1 over x, it ends up being a factor of x. These x's cancel, and so we can write down the solution. The integral of sine is negative cosine, so we'll have negative x cosine x plus c times x. In problem 3, we also have a first order linear differential equation, but this time we have an initial condition, y of 1 equals 0. So that means that we need to use this initial data to solve for the constant of integration after we find the general solution to the differential equation. We already know the integrating factor from the last problem. The integrating factor is 1 over x. We don't need to do that again. And if I give you something like this on the exam where you get the same integrating factor on 2 problems, you don't have to do the work twice. Now, the general solution then is going to be 1 over mu, that's x, integral of mu q dx plus c over mu. Again, the x's cancel here, and we're just integrating e to the x. So we get y is x e to the x plus cx. It's at this point that we need to use our initial data. Using the initial condition, 0 is going to be y of 1. If we plug in 1 for x, we'll end up with e plus c, which means c is minus e. It follows then the solution is y equals x e to the x minus e times x. As the differential equation y prime equals y squared plus 1 divided by xy. Separating the variables and expressing this as dy over dx, we'll have y divided by 1 plus y squared dy is 1 over x dx. We integrate both sides. On the right-hand side, that's easy enough. It's the left-hand side that needs a little bit of work. The derivative of the denominator with respect to y is 2y. To put the integral in the form f prime over f, I need a coefficient of 2 in this location here. We get what we want. We just need to pay for it by putting a 1/2 out front. Once we've done that, we get the log 1/2 log absolute value 1 plus y squared equals natural log absolute value of x plus c. And that solves the problem. Make sure you get these integrals right. Make sure you put in these absolute values. I'll mark you off if you don't. These absolute values on the left really don't affect anything because 1 plus y squared can't be negative, at least over the real numbers. Which means that these absolute values are superfluous. You can put parentheses instead. But the absolute values on the right are absolutely necessary. In problem 5, we have dy dx equals 2 times the square root of 1 minus y squared over x squared plus 1. Now, we can separate the variables pretty simply. We'll have 1 divided by the square root of 1 minus y squared dy equals 2 divided by x squared plus 1 dx, and we'll integrate then both sides. I want you to be able to recognize both of these integrals. On the left, this is an integral I asked you to remember. This one gives you arc sine of y. On the right-hand side, this 2 can come out of the integral and we can replace it with 1. You should recognize this as the 1. That's the one I asked you to remember. That's arctangent of x plus c. And that is the solution to the differential equation. For problem 6, we have dy dx equals x squared minus y squared divided by 2xy. You should be able to identify this as homogeneous. The homogeneous method begins by making the substitution u equals y divided by x, and that implies that y prime is x u prime plus u. In the method that we developed for solving these equations, we replace x by 1 and y by u everywhere in the right-hand side of the equation. We'll end up with x u prime plus u equals 1 minus u squared divided by 2u. We'll move this term to the other side and have x times du dx equals 1 minus u squared over 2u minus u. We're subtracting fractions. In order to subtract fractions, you need to have a common denominator. So we'll multiply this second term by 2u divided by 2u, and this simplifies as 1 minus 3u squared divided by 2u. The differential equation that results is separable. Separating the variables, we'll have 2u divided by 1 minus 3u squared du equals 1 over x dx, and then we integrate. The derivative of the denominator on the left-hand side is negative 6u. The numerator is 2u. So I want this to be negative 6. To pay for it, I'll have to put a negative 1/3 out front. You can see then I get negative 1/3 log of the absolute value of 1 minus 3u squared equals log absolute value of x plus c. We're not done until we substitute back for u, keeping in mind that u is y divided by x. So the answer is going to be negative 1/3 log absolute value 1 minus 3 times the quantity y divided by x squared equals natural log absolute value of x plus c. And that is the solution. For problem 7, we're asked to solve negative x plus y dx plus x plus y dy equals 0 using methods for exact equations. In order to do that, we'll test to see whether or not it is exact. My is 1, nx is also 1, and since those are equal, it is exact. Now, one version of the function f will be the integral of negative x plus y with respect to x. Just take this and integrate it with respect to x. You get negative x squared over 2 plus xy plus an arbitrary function of y. You don't get a constant of integration, you get something that's constant relative to the variable that you integrated with respect to, but not necessarily with respect to y. This could involve y's. We also find f is the integral of x plus y with respect to y. That gives us xy plus y squared over 2 plus an arbitrary function of x this time. We have two versions of the function little f. We reconcile those. To reconcile these functions, note that the solution is negative x squared over 2 plus xy plus y squared over 2. Those are all of the terms down here equal to a constant. And this is the family of solutions. Notice that these solutions are all conic sections, but because they have this xy term, they are rotated conics. It might be interesting to figure out what kind of conic sections these are. Just so that you can recall some of your learning from pre-calculus. In pre-calculus, you were told that if you have equations of the form ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, then you're dealing with a conic section. And you can figure out what kind it is by looking at b squared minus 4ac. If that's less than 0, then it's an ellipse. If it's equal to 0, it's a parabola. And if it's greater than 0, it is a hyperbola. Do you remember this from pre-calculus? Let's apply that to these functions here. In this case, b squared minus 4ac will be 1 squared minus 4 times negative 1/2 times 1/2. Because we have a minus times a minus, whatever this is, it's positive, and therefore we have a hyperbola. For problem 8, we have the differential form y dx plus negative x plus 2y dy equals 0. In this case, my is 1 and nx is negative 1, which means this differential form is not exact. However, there are formulas given on the handout that you can use to determine an integrating factor that will make this thing exact. Both of those formulas use my minus nx, which in this case is going to be 1 minus negative 1, or in other words, 2. You have to divide either by the coefficient of dx or the coefficient of dy, whichever one gives you only one variable. In this case, we'll be multiplying by 1 over the coefficient of dx, which is m. This means we'll use the formula d mu dy equals minus my minus nx over m times mu. In this case, that's negative 2 divided by y all times mu. This differential equation is separable. We can separate the variables as follows. 1 over mu d mu equals negative 2 over y dy. We then integrate both sides. This gives us log mu. Remember, no plus c's, no absolute values when finding these integrating factors, minus 2 log y. We need to bring this negative 2 up before we exponentiate. We'll get the log of y to the power of negative 2. Exponentiating, we find the integrating factor is 1 over y squared. Simplifying, we have 1 over y dx plus negative x over y squared plus 2 over y dy equals 0. Is this exact? The derivative of 1 over y is negative 1 over y squared, and nx will be negative 1 over y squared, and therefore the equation is now exact. To find our function little f, we need to integrate 1 over y with respect to x. This gives us x divided by y plus an arbitrary function of y. Alternatively, we need to integrate negative x over y squared plus 2 over y dy with respect to y. This gives us x over y plus 2 log absolute value of y plus an arbitrary function of x. Reconciling these two answers, we see that x over y must appear, but so must twice log absolute value of y, and that has to be equal to a constant. This gives us the solution to the differential equation. In problem 9, you are asked to perform 2 iterations of Eulers' approximation method to the initial value problem dy dt is equal to the square root of 1 divided by y minus 1, where y of 0 is equal to 1/2. Recall that for Eulers' method, the new y is going to be the old y plus h times the function at the old point, xn, yn. In this problem, h is chosen to be 1/10. We need to do 2 iterations. We start with y0, which is y of 0, which in this case is 1/2. The first iteration of the method says y1, that's choosing 0 for n in the formula for Eulers' method. It's going to be y0, which is 1/2, plus h, which is 1/10, times the square root of, let's see, 1 divided by 1/2, minus 1. Let's simplify this. 1 divided by 1/2 is 2. 2 minus 1 is 1. So we end up with 1/2 plus 1/10. 1/2 is 5/10. Plus 1/10 we get 6/10, which reduces to 3/5. The second iteration begins with the old value, 3/5, plus 1/10 times the square root. You have to take the reciprocal of the old value. This reciprocal of 3/5 is 5/3. And this is where we're going to leave this. On the last problem, number 10, you're given various options. Option A is that the equation is linear. B is non-linear. C is separable. And D is homogeneous. On the first problem, we're given y prime equals y times 1 plus y squared. Is this linear? Well, it has y squareds and a y times that. Even you end up with a y cubed when you distribute. This can't be linear because we have powers on the unknown function y. So this is nonlinear. However, it is separable. We can separate the variables. This function is a separable function of x and y. It is not homogeneous, so this is it for part 1. For part 2, we're given the differential equation y prime equals 2x minus 3y. This problem is definitely linear. Y and its derivatives appear in separate terms to the power 1 in the numerator. And so this is linear. It is not separable, and it is not homogeneous, so that's it. On part 3, we're given y prime equals 1 minus the natural log of x times y. Y and its derivatives appear in separate terms to the power 1 in the numerator, so this is linear. It is not separable, and it is not homogeneous, so again, that's it. On part 4, we have y prime equals y divided by x. Y and its derivatives appear in separate terms in the numerator to the power 1, and so this is linear. It is also separable, and since this is a homogeneous function of degree 1, and this is a and since the numerator and denominator are both homogeneous functions of degree 1, this is also homogeneous. On part 5, we have y prime equals negative x divided by y. You can see that y on the right-hand side is in the denominator. That makes this decidedly nonlinear. However, That doesn't mean it's not separable. It is separable, and it is still homogeneous. And now for part 6, we're given y prime equals x squared plus y squared over x squared minus y squared. Yeah, all those squares, divisions, multiplications, this is definitely going to be nonlinear. It is not separable, but both numerator and denominator on the right-hand side are homogeneous functions of degree 2. So this is homogeneous.